Hello everyone. So today we'll be discussing cluster analysis. Cluster analysis is basically a method by which we try to divide the objects that we have or people that we have in different groups. Okay. Cluster analysis comes under what is typically known as unsupervised learning. Why unsupervised learning? Because the data doesn't give us the groups directly. What we do is, depending on what we are observing, we try to divide the data into different groups. So it it may happen that for some of us some variables are important, so we get some groups. For other people other variables are important, and using those variables they'll get different groups. That is possible. So rearrangements and shufflings of groups, etc. is possible. We are trying to create our own groups as per the variables that are important to us. So to explain this further, let me give a simple example. Let us consider different fruits. So what are the ways in which you can classify a fruit? The simplest way can be size of the fruit. Whether the fruit is big or small or medium, if you want multiple categories. You can maybe group fruits as per the size, or you can maybe group fruits as per the taste, whether they are sweet or sour. Okay. Or you can maybe group the fruits by the season. Okay. Or some people might say by the number of seeds that they have. So do they have any seeds, and if yes, do they have a single seed or multiple seeds? Or whether the fruits go as a single fruit or in bunch. Then some people might say that okay, we can decide on the basis of how they are eaten, means whether they are peeled before they are eaten or not. So with peel or without peeled. Some more practical people might say okay, let us group by price. So see, even without thinking much, we could come up with at least 7 criteria by which I can group fruits. Okay. Sometimes you may not want to work with just one criterion. You may want to work with multiple of them. So you may want to consider say size, taste, season, seeds together. Okay, and then decide okay, which fruits are more similar to each other in some sense, which fruits are more different, and so on. Okay, so cluster analysis kind of works in this way. So you collect data on many variables, and using those variables you try to decide are there any inherent groups in the data. Okay, the groups are not given to you, groups are not indicated in the data, but using the variables you try to see are there any inherent existing groups which can be formed on the basis of the data that we have. And why do we need that? We need that to see what is similar and what is dissimilar. Okay, and that might help us when you want to, when you don't have something and you want to substitute for it. For example, one of my students did a project on clustering of players, cricket players. So what can be application of it? Okay, so suppose you want to buy a team, you want to create a team for IPL, and you are interested in a particular player, but that player is not available for some reason. Then who can be a replacement? So looking at the performance of the players, you can identify which player is kind of closest to the player that you wanted. So okay, it's a good replacement. Okay, it's a good substitute. Same thing can be done with the mobile phones, let's say. So you want to buy a new mobile phone, you do a survey in the market, you know your requirements, so you choose and use heroin on a particular model, but unfortunately that model becomes out of stock. Okay, so you want something which is next closest. So you have to know what is closest to the model that you want. Okay, so some sort of such closeness can be measured via this process of cluster analysis. So today we are going to discuss some theory behind that. There are two major categories or ways in which cluster analysis can be carried out. So they are known as hierarchical and non-hierarchical. As the name says, Hierarchical means there is some sort of order in it. Okay. So in hierarchical there are again two possibilities. There is something called as agglomerative and then another one called as divisive. So what do you do in agglomerative? You start by saying that all your objects, suppose you have n objects, you again have multivariate data. So you have n observations and on each of these observations you are recording p different things. So you have p variables. So you have n observations. So in agglomerative clustering, you start by saying that all the n objects are in their own groups. So n objects, they are equivalent to n groups or n clusters. Then at the next step, you locate which two objects are closest to each other and you join them. Okay, so you put two objects in one group, everyone else remains separate, everything else remains separate, and you have n minus 1 groups. Then in the further next step, you treat this as one object and other n minus 2 things as another object, and you try to see among these n minus 1 objects which two are closest to each other. You try to join them and you will get n minus 2 objects. And the process continues till you finally end up with all the n observations in one place. Okay, so this is agglomerative. You kind of go on aggregating things together. Divisive hierarchical clustering works in exactly an opposite manner. You start with all the n observations in one group. Then you locate the one which is most dissimilar, you throw it away. And so you have a group of n minus 1 here and this one is separate. Then among these n minus 1 you locate the most dissimilar one and throw it away and so on. And you go on doing this till you have everyone as a separate object. Okay. Sometimes instead of just throwing one away, you divide them into two parts, two as heterogeneous as possible parts. So it doesn't have to be half. Then each of these you further divide into two parts and so on. Okay. Now why the name hierarchical? So as I said, there is a hierarchy or order to it. In the sense, so in this step, if you have put these two objects together, and because you are an agglomerative, things are going to get combined further. So these two stay together till the end. If they come together at this step, in all further steps, they must stay together. They cannot get away from each other. Okay. Similarly, in the divisive case, if you have separated things, so if suppose you have some O1 here and some O5 here, so at this stage they got separated, then they should always stay in the separate groups. They cannot get together again. Okay, so in that sense, this is hierarchical. So whatever has been done by the earlier step, that is preserved, that is protected, that is respected, and then the next step is carried out to enhance it further or change it further. Okay. On the other hand, in non-hierarchical, that doesn't happen. So a typical example of non-hierarchical clustering is k-means clustering. We'll see what it is. So in k-means clustering, what happens is you fix the number of groups in advance, that is k, and you have n objects. So at first step, you randomly divide them into k groups. Okay, so you have some objects here, some objects here, some objects here, and some objects here. At the next step, you again reshuffle these groups to get again k new groups. But what happens is, because you are completely reshuffling and getting exactly same number of groups, the relationships are completely destroyed. What do I mean by that? Things which are together in this step might go into two different groups. Okay. On the other hand, things which were in two different groups here might end up in one group here. Okay. So the shuffling tells me that no association is permanent. Okay. Some objects are together, some are away from each other. In the next step, this might change. So in that sense, this is non-hierarchical. Whatever happens in the earlier state is not directly preserved. Okay. Another important difference between hierarchical and non-hierarchical is, in hierarchical, the number of clusters goes on either decreasing or increasing. So in agglomerative, it goes on decreasing. In divisive, it goes on increasing. Whereas here, number of clusters remains the same throughout. in non-hierarchical. Okay. Now one question that some of you might have started thinking about is, I said in agglomerative, you start with n objects as n group and go on doing this till you have everything in one group. Similarly in divisive I said, you start with all of them together, you go on dividing until you have everything separate. Now this seems kind of pointless, right? If I anyway finally want everything in one group, why to go this charade of carrying out so many steps? Why not just put everything in one group? Similarly, if you at the end want everyone separate, why to go step by step? Just throw everything away and put everyone separate. So the thing is, yeah, the procedure is applicable till you go to the last step, but after reaching the last step, you see how the changes have occurred, means how the groups have split or how the groups have formed, and then you decide at what level the groups are at the similarity level that is intended by you. Okay, so it's kind of like what happens in a new group. For example, when you people met on your first day of college, you may not know each other, so you are like kind of 30 different people. Let's say if there are say 30 people in your class, so you are 30 different people. Then over a period of few days, some associations started forming. So people who sit together, or people who probably travel together, or people who are in the hostel together, something like that. Some associations started forming and some small groups started forming. At the end, generally more or more these associations would keep on growing, and whenever there is a fest or something, or there is a trip or something, all of you might become a part of one group and you would do things together. You would work towards these things together. Okay. However, you know that there might be some inherent smaller subgroups, of course not as independent as they were at the beginning, but there might be some smaller subgroups which work better within themselves. Okay, and when they are kept away from each other. Okay, so even if it is possible to carry out clustering till very end, and we do carry out till very end, but then we come back and see what is the most optimal configuration. So you have not put too many things together so that the group is heterogeneous, and at the same time you don't have too many distinct groups. Okay, so you have kind of similar things together. So at that step you stop. So generally the hierarchical clustering is represented via some sort of branch diagram, which is known as dendrogram. So you go on dividing it like this. Okay, you might have seen such types of charts even in say phylogeny or something like that. And then at some stage you decide where to stop. So if you decide you have to stop here, you would be left with only two groups. On the other hand, if you decide you have to stop at this stage, you will be left with 1, 2, 3, 4 groups, etc. Okay, and this deciding where to stop is dependent on the similarity level that we want. Okay, now I've been using terms objects are close to each other, objects are similar to each other, objects are dissimilar to each other, and so on. But what do I mean by that? What do I mean by apple and orange are similar to each other or they are dissimilar to each other? So we need some way of quantifying this notion of similarity or dissimilarity. Okay, so we introduce what is known as a distance function, which is also known as dissimilarity function. Okay, so given any two objects, we can find distance. This is not a physical distance. This is distance in terms of closeness or similarity. So we try to find distance between them using the variables that are of interest to us, and then we use that distance to decide whether they are similar or dissimilar. So when you say you are going to have a distance, what are the requirements? So generally, distance function is defined from some set to R. R is set of real numbers. So you can compute distance between objects which are in some way in a single group, so that you measure same variables on them. Okay. And of course you need two objects, then only you can compute distance. You can't compute I mean, if you want to compute distance from it, the object itself, you would have to write it as fxx. Okay. So what are the requirements? General requirements. Distance would have to be non-negative. Okay. You can't have a negative distance. Then secondly, distance has to be symmetric. Okay, we are not considering one ways, etc. So because this is not a physical distance, so distance has to be symmetric. Thirdly, it has to be reflexive. Reflexive in a sense, distance of an object from itself should always be 0 because you are most similar to yourself. And there is another important property of distance function which is known as triangle inequality. So what does the triangle inequality say? That distance between two objects xy is less than or equal to distance between xz plus zy. So you have x here, you have y here, and suppose z here. So the distance required to go directly from x to y, it's supposed to be straight line, is definitely less than distance required from x to z plus z to y. See, even if z is on this line, then in that case that would be exactly equal. So it is either less than or equal to. And you might have seen why the name triangle inequality, because it is actually based on the fact that sum of any two sides of a triangle is always greater than the third side. Okay. So we can introduce various distance functions which satisfy these properties and then decide which objects are similar to each other or dissimilar to each other. Some commonly used distance function include Euclidean distance, so Euclidean distance is a straight line distance or a aerial distance in some sense. So how is it defined? It's basically the closest distance between any two objects. How is it defined? So let me consider, suppose I have bivariate data. You have one object here, you have another object here. Euclidean distance between them is this straight line distance. Okay. So how do I compute it? So suppose the coefficients, the coordinates of these are a1, b1 and these are a2, b2. Okay. Then this straight line distance, how can I compute? I can first join these points by a triangle. Okay, this is a right angle triangle. So I know this is b2, this is b1, then this is a1 and this is a2. That much I know. So this side is of length a2 minus a1, this side is of length b1 minus b2, right? And how do I get the diagonal? Because I want the diagonal. So diagonal we know by Pythagoras, it will be a2 minus a1 whole square plus b2 minus b1 or b1 minus b2, doesn't matter, b2 minus b1 whole square and then square root of that. Okay. So Euclidean distance between any two objects would be given in this way. So if you say that you have two vectors x and y, where x itself is say x1, x2, xp and y is say y1, y2, yp, so both are p variate, then distance between them would be square root sum over xi minus yi whole square. Okay, so this is a Euclidean distance or straight line distance. This is most commonly used distance function when you have continuous variables. Okay, there is another distance called as Manhattan distance or city block distance or taxi cab distance? So what do I mean by city block distance or taxi cab distance or Manhattan distance? So we again have these 2 points. Euclidean distance measures direct distance. But what if I am not allowed to travel directly and I am allowed to travel only in straight line? Okay. So the distance from these to these points becomes this. So it would be actually A1 minus A2 plus B1 minus B2 in the earlier notations. Okay, mod of course. Okay, so in general, distance between xy is summation mod of xi minus yi for Manhattan distance or city block distance. Can you guess why it is called as Manhattan distance or city block distance or taxi cab distance? It's kind of like if you have a planned city where all the roads are intersecting each other only at 90 degrees, then you can't travel directly along a slanted road. You have to go like this. Okay. There are many other distance functions for continuous data. For example, Minkowski distance, then normalized distance, which always stays between 0 and 1, but we won't go there. We would introduce one distance function especially for categorical data. So it is kind of a binary distance function. You can apply it either to the vector level, means you would say that the two vectors have 0 distance if they match completely, or they have distance 1 if they don't match at all. But then if suppose for a vector of if suppose we are talking with vectors of size 5, t equal to 5, and if in there are two vectors where 4 objects match, 4 variables match out of those 5, and there is another pair of vectors where only one variable matches, then in such case you need to distinguish between those two. So we introduce binary distance but variable wise or component wise. So what we do is distance between any two objects x and y would be number of mismatches, either just the number of mismatches or you can have number of mismatches upon p. So upon p is optional. What do I mean by this? Number of mismatches. So let me take a say fruits. So I have say mango and grape, and I'm talking about say size, color, taste, and what else? How many seeds do they have? Okay, so suppose size, this is medium, this is small, color, this is yellow, this is green, taste, this is sweet, this is mostly sour, number of seeds here is 1, number of seeds here is 0. Okay, if I am assuming seedless grapes. If you want grapes with seeds, then we can take this to be 1. Let's take it to be 1. Now we can see that out of 4 variables, this variable is matching. So the distance would be number of mismatches, that is 3, or 3 by 4 if you want by p. Okay. So this is a distance function based on binary distance, and it is mostly used for categorical data, especially when you have nominal categorical data. Nominal means there is no order in the category. Okay. For ordinal category data, you can use Manhattan distance. Okay. Now with these distance measures in our hands, we have to go further and define one more new concept called as linkage methods. So what do linkage methods do? So the distance function tells you how to compute distance between two observations. But We saw in the preliminary discussion on clustering that sometimes you might have two clusters. Okay, so there are few objects here and there are few objects here. Or you might have one cluster and one single observation. Okay, so you have a cluster here and you have a single observation. Then, how to compute distance between such groups or between a group and a single individual? Okay. So suppose we have two groups. In first group, suppose I have only two objects A and B, and in the second group I have suppose three objects C, D and E. So I want to compute distance of first group with the second group. So how do I do that? We do that by combining the individual distances in some way. Okay. So what are the things that easily come to your mind? Think. Okay. One of the easiest ways would be what is known as single linkage. So what do we do in single linkage? We take the smallest possible distance. Okay. So single linkage between distance between these two groups, let me call this group 1 and group 2, would be distance between group 1 and group 2 would be minimum over, that is smallest, all possible distances. So AC, AD, AE and BC, BD, GE, BE. Remember, when I am saying all possible, I am not considering distance between A and B because they are in the same group. So for me, practically now they are only one object. Similarly, CDE, they are practically one object. So I am worried about only distance from one group to other group. Okay, so single linkage method says compute the distance as the smallest possible distance. Okay, then of course another version would be the maximum. So that is known as complete linkage. Okay, so complete linkage says distance between group 1 and group 2 would be maximum of AC distance between AD distance between AE, then distance between BC, BD and BE. Okay, so this is complete linkage, maximum distance. So you consider all possible distances and take maximum. Of course, minimum and maximum are kind of extreme. So you have something called as average linkage. So in average linkage, what we do? We take the average of the distances. So distance between G1, G2 would be distance AC plus AD plus AE plus BC, BD, DE and all this entire sum divided by 6 because there were 6 pairs. Okay, so this is average distance, and there is one more which is commonly used, that is centroid distance. Centroid linkage. So what does centroid linkage says? It says compute the centroids of each group. So centroid of first group would be if it's univariate, then A plus B by 2, even in multivariate it would work. And centroid for second group would be C plus D plus E divided by 3. Okay. So, and in centroid linkage, what you do is you say that distance between group 1 and group 2 is same as distance between, this is same as distance between C1 and C2. Okay. So this is centroid linkage. So these are four methods which are used in linkage methods. There are some other methods like median linkage or Ward's linkage. Ward's linkage is also quite commonly used, but there is no direct formula for it. You try to form the groups in such a way that the homogeneity is maintained as far as possible. Okay, and across groups there is as much heterogeneity as possible. Okay, let me stop here. Thank you.